How often have you wondered how rain is formed? Actually, there are two ways we've learned about. As you know, you need a cloud. Here in Arizona, it's wintertime. The sky's clear. There aren't any clouds around. So let's go to the tropics. These clouds, speeded up in time, are forming and dissolving over a warm ocean. Their bottoms are about 1,500 feet above the water. Most of these clouds never produce rain, but sometimes they keep growing until they are thousands of feet deep, and rain showers come pouring out. How does this come about? To begin to answer this question, we must know the difference between cloud droplets and raindrops. We can capture actual cloud droplets and photograph them and study them. But before we do so, let me show you how we get such pictures. This is a glass slide coated with a thin layer of oil. The steam coming out of this flask produces a cloud of water droplets. If I swish the slide through the cloud and then look at it under the microscope, I can see small droplets immersed in the oil. The oil keeps the droplets from evaporating, so we can photograph them. Droplets collected in this way appear to be quite close together because we move the slide through the cloud. In a real cloud, they are much further apart. Here is a photograph of droplets sampled from a natural cloud. In reality, the smallest droplets are about as big as the point of a needle. They are about 10 microns, or 1/100th of a millimeter in diameter, while the larger droplets are about 40 microns across. In a cloud over the ocean, there are about 500,000 such droplets in a volume the size of a basketball. These droplets usually form on submicroscopic salt particles, which tend to collect water molecules from the air. We call such particles condensation nuclei. Here under high magnification are condensation nuclei that have been deposited on a single thread from a spider's web. These nuclei are actually much larger than those usually found in nature. The vast majority of nuclei are too small to be seen even under the microscope. However, over the oceans, we do find a few condensation nuclei this large, but they seldom are more numerous than about 1 in 10,000. We call such particles giant nuclei. The particles we are looking at are in this chamber, where moisture in the air can be controlled by means of this pump and bubbler. When the wet air is let in, you see droplets growing because water molecules condense on each particle. As a droplet grows, the nucleus dissolves and the salt solution becomes weaker. As the solution becomes less salty, it loses its attraction for water molecules. For that reason, and other more complicated ones, the droplets reach a maximum size. This droplet is about 50 microns in diameter. It is a large cloud droplet, but still not very big. In fact, this dark thing, which looks like a log, is really a man's hair. So most cloud droplets are certainly much smaller than raindrops, which you can see with your naked eye. Here's a gadget we can use to measure raindrops. It's a frame covered with a nylon stocking. The mesh has been covered with powdered sugar. We can watch a water drop falling through the mesh in slow motion. leaves an image whose diameter is very close to the diameter of the water drop. Here's a mesh which was exposed to rain. A centimeter rule shows that the drops which left these prints were about 2 millimeters across. As a matter of fact, raindrops are about 100 times larger than cloud droplets. This is a tremendous difference. For example, if this balloon, which is about 1 meter in diameter, represented a scaled-up raindrop, a cloud droplet would be the size of this marble, which is 1/100th of a meter or a centimeter in diameter. Incidentally, a condensation nucleus on this scale would be the size of this BB. So as these scaled-up models indicate, there's a lot more water in a raindrop than there is in a cloud droplet. 1 million times more. To find out how cloud droplets turn into raindrops, let's visit the National Center for Atmospheric Research, where Pat Squires has an experiment to show us.
How large can cloud drops grow by condensation? That depends on how many there are to share the water which is present. Look again, and you will also see that it depends on the size of the nucleus on which the droplet forms. Notice how the growth on these giant nuclei is very rapid at first, but then slows up. In real time, their growth took place in a few minutes. 20 minutes later, they are bigger, but not by much. They are still many times smaller than the average raindrop. To see how the vast majority of very much smaller droplets grow, we set up a different type of experiment. Here is an apparatus in which it is possible to reproduce the formation of a cloud in much the same way as it happens in nature. The bottom of this flat box is made of glass, and this is covered with a thin layer of water. Through this hole in the side of the box, there enters a very narrow and intense beam of light which passes across the box above the layer of water. This is the top of the box. It is made of brass and lined on the inside with a wet cloth to supply moisture. Through this hole, we introduce samples of air which we wish to study. The top of the box is heated to a few degrees above the temperature of the glass bottom of the box. When these two parts are placed together, the air trapped between them forms a cloud. By introducing through this tube the various samples of air containing more or fewer nuclei, and by varying the heating of the top plate, it is possible to model the formation of different types of clouds. Now we'll turn off the lights and I'll introduce a sample of air. This sample contains many nuclei. Therefore, many droplets share the moisture in the air. To determine how big they are, we measure how fast they fall. Such measurements tell us that these drops are quite tiny. Now I'll clear the box and put in a sample containing fewer nuclei. Fewer droplets form, and again from careful measurements we have determined that on the average these droplets are larger than those in the previous sample. But even these somewhat larger droplets are still many times smaller than the average raindrop. We know that clouds like these over the ocean contain fewer but larger droplets. But still, by condensation alone, none of them, not even those formed on giant nuclei, can ever reach the size of raindrops. What is needed for rain to form is some way for a few drops to grow much larger than all the others. This can happen in an entirely different way, which is being studied here by Doyne Sarter.
In my studies, I'm trying to find out how these tiny cloud droplets can combine together to form raindrops. This sweating glass is a simple illustration of our thinking. Let's look at it in time-lapse photography. Have you ever noticed how at first the glass sweats uniformly with tiny droplets distributed evenly about its surface? In a few places, though, larger droplets form and start to fall down the sides of the glass. As they trickle down, they grow still larger by merging or coalescing with numerous smaller droplets in their paths. The question is whether this sort of thing can happen in an actual cloud. The important thing to remember is that these cloud droplets are extremely tiny, smaller even than these particles of chalk dust. These dust particles hardly seem to fall at all. It's the same with cloud droplets. They're so tiny that it would take them roughly 10 seconds to fall across this light beam. In a cloud where the air is usually rising, they may actually be carried upwards. But not all droplets will be carried upwards at the same speed, because not all droplets are the same size. So in a cloud, this relative motion of droplets may allow them to collide and coalesce, growing large enough to fall out of the cloud. The problem, as Pat Squires indicated, is that the vast majority of droplets are quite small, too small, in fact, to start this collision coalescence process. So the critical problem is what happens when two droplets come close together. We can illustrate this on a much larger scale using this tank of oil and large water drops. The resistance the oil offers to these large drops simulates the resistance the air offers to cloud droplets, which are much smaller. In fact, if we could put ourselves on the same scale as cloud droplets, this is about the way a small volume of cloud would look. The speeds with which these drops fall are very close to the speeds with which cloud drops fall in air. Now I'll release a small drop and follow it with a larger one. Here it is again. The larger drop falls faster and passes the smaller one. Note that the large drop doesn't touch the small one, but pushes it out of the way. This time watch and you'll see the smaller droplet roll around the larger one. We believe that cloud drops of the proper size can coalesce in air, but we cannot make these larger water drops coalesce in oil without introducing another force, electrical in nature. The atmosphere, and clouds in particular, carry electric charges, as you well know from seeing lightning. These electric charges and the electric fields they create may have an effect on the coalescence of cloud droplets. Let's see what this effect might be. I will place an electric charge on these plates so that there is a vertical electric field between them, similar to that exists in clouds. Now, when I form two drops, they collide in an electric field. And you see these drops coalesce. When the electric field is applied, they coalesce nearly every time. The question is, do things happen like this in the atmosphere? This is a hard question to answer. It's not easy to see cloud droplets actually collide in the air. They're so very tiny. But we can see larger water drops collide in the air. These are hypodermic needles which we vibrate at a constant frequency with small radio loudspeakers. This breaks up the streams so that individual droplets collide in front of the camera. Here we see the drops in slow motion. Some can be seen to bounce off and others to coalesce. If we apply an electric field with this electrically charged rod, many more coalesce, as you see here. Now the field is off, and again they tend to bounce off one another more often. Let's try this again with the electric field. The droplets bounce because of an extremely thin layer of air between them. The electric field provides a force of attraction between the drops, causing the water to break through this thin layer of air and allow the drops to combine. With the proper conditions, which have to do with the flow pattern around the droplets, their size, the presence of electric fields, and other effects we don't fully understand, drops do collide and coalesce. In a cloud, this happens on a gigantic scale, with drops moving up and down with the air currents, hitting each other, sometimes bouncing and sometimes merging. On the whole, the big drops get bigger and bigger as long as there is more cloud to fall through, until from the base of the cloud it starts to rain.
So far, we've been talking about how rain gets started in warm clouds over the tropics. The same thing can happen in clouds over the land if there are enough large cloud droplets to start the coalescence process. From sampling clouds like these, though, we know that large droplets are not always present in great quantity. Instead, very large numbers of small droplets are found in clouds over the continents. These droplets form on nuclei which come from forest fire smoke, and also smoke from industrial chimneys and the millions of other exhaust pipes that surround us. We know from air samples that very few giant nuclei are contributed by these sources. Most continental nuclei are too small to give rise to those large droplets which initiate the coalescence process. Therefore, we must find another method. Let's begin by looking at this large thunderhead or storm cloud. The top of this cloud appears very much different from the one over the ocean. Also, the cloud is very large and extends to great altitudes. Even though the ground below the cloud might be very hot, the temperature in most of this cloud is below 0 centigrade. Here is a photograph of cloud particles collected by an airplane which flew into such a cloud at an altitude of about 20,000 feet. We see that in addition to the water droplets, there are these apparently solid objects, tiny pieces of ice. It's not surprising that ice forms in clouds where the temperature is below 0 centigrade. In fact, clouds like this, which I'm sure you have all noticed very high in the sky, are so cold they are made of ice almost entirely. These cirrus clouds, which may last for a long time, have a wispy, finished look. The top of this large storm cloud also has a wispy appearance. it is important to recognize that in the early stages of the cloud, there are comparatively few ice particles, even though temperatures might be as low as minus 15 to minus 20 degrees centigrade. Apparently something in addition to low temperatures is usually required to freeze cloud droplets. Just as there are condensation nuclei, you might have guessed that there are ice nuclei, which lead to the formation of ice crystals. The trouble is, ice nuclei are not very abundant in the atmosphere, but a relatively few ice particles can have important effects on the structure of a cloud, because the ice crystals can grow by collecting water molecules directly from the air. These ice particles are growing in this way. In a cloud, there might be one such particle for every million cloud droplets. As the ice particle grows, water droplets evaporate. The water molecules added to the air by the droplets then freeze out on the ice particle. These ice particles have grown to about 200 microns, or 1/5 of a millimeter across. They are many times larger than the average cloud droplet. Once an ice particle reaches this size, it can fall through the cloud and grow at an even faster rate. In falling, the ice crystal will run into many cloud droplets. When the droplets hit the ice, they freeze. Several ice crystals, too, can merge together to make a larger particle. Such interlocking crystals are what we commonly call snowflakes. Though ice and snow may be forming in this cloud, it can only reach the ground that way when the air stays cold below the cloud. Most of the time, in clouds during the summer, the snow melts before it falls out of the cloud. In fact, sometimes the flakes melt far up in the cloud, in which case the drops formed can continue growing by the coalescence process. In either case, large clouds like these usually bring heavy rain. In this film, we have dealt almost entirely with cumulus clouds like these, but we believe that the same kinds of processes go on in the stratiform clouds, which can frequently bring large amounts of rain or snow. In summary, there are two ways by which precipitation can be formed. First of all, the cloud itself develops by the condensation of water vapor on the countless numbers of tiny condensation nuclei, which almost always are present in the atmosphere. However, condensation alone will not lead to rain. It is necessary for another process to occur. In one, large cloud droplets are required to start the coalescence of cloud droplets into raindrops. This process occurs most frequently over the warm oceans, but it can occur over continents as well. The second precipitation mechanism occurs when clouds become very cold. Ice nuclei cause the formation of ice crystals, which grow quite large at the expense of the water droplets. In this way, they may grow large enough to fall as snowflakes, or if the lower part of the cloud is warm, they melt into large water droplets and continue growing by coalescence. The fact that sometimes large condensation and ice nuclei are not present naturally in large numbers has led us to try to modify clouds by seeding them with man-made nuclei. But that's another story.